All right, today we're cracking open the engineering playbook on something really challenging. We're going to transform this everyday cement mixer into a seriously advanced high-voltage hybrid. So let's get right into the nuts and bolts. You've seen this truck everywhere, right? It's literally the backbone of our cities, a fixture at every single construction site. But behind that tough exterior, there's this huge, expensive secret, a massive inefficiency that's just burning money, polluting the air, and making our cities louder. And it all comes down to one simple, kind of crazy reason. And that number is 40%. That's right. On a typical job site, this truck spends almost half its time sitting still, engine screaming away at high RPMs. And for what? Just to keep that big drum spinning. It's literally torching fuel for the sole purpose of mixing concrete. That right there, that's the core engineering challenge we're tackling today. Okay, so here's how we're going to break this down. We'll look at the problem with concrete, then dive into the smart hybrid solution we've designed. After that, it's all about the high-voltage backbone, the global safety maze we have to navigate, and the power coordination symphony that makes it all work together. And then, we'll wrap up by looking at what's next for heavy machinery. All right, so the whole game changes with one key strategic decision. We have to completely sever the link between the diesel engine and that mixing drum. The objective here is simple, but honestly, it's revolutionary for this industry. We're talking about silent, zero-emission work on site, all while making absolutely sure the quality of the concrete is perfect. And this is the heart of it all. We call it a P2 hybrid with an ePTO. So what does that mean? Well, the P2 part means we've put an electric motor right smack between the engine and the transmission. That motor then powers what we call an electric power takeoff, or ePTO. And that's what spins the drum, using only battery power. And the magic here? The diesel engine can be completely shut down, but the concrete keeps mixing. It's a total game changer. So this system is incredibly flexible. Look at these modes. First, you get to the job site, you shut the engine off, and boom, you're in electric operation. Quiet, zero emissions, just mixing away. Then, on the road, the diesel engine is not only driving the truck, it's also acting as a generator, topping up the battery through that P2 motor. And my favorite part? Regenerative braking. Every time this massive truck slows down, all that momentum gets captured and turned back into useful electricity. It's just a brilliant, self-sustaining loop. Okay, let's get into the hardware that makes all this magic happen. The foundation for everything is a 400-volt power electronics platform. You can really think of it as the truck's own private high-voltage power grid. It's the backbone that everything else relies on. So the architecture is actually split into two different worlds living side by side. You've got the 400-volt high-voltage platform, which is the muscle. It does all the heavy lifting, powering the motors. Then you have the 24-volt low-voltage platform, that's the brain, handling all the controls, the lights, the crucial safety systems. And the component that lets these two worlds talk to each other, that's the DC to DC converter. It's the critical translator, and without it, nothing works. But here's the thing. Picking the right DC-DC converter isn't simple. It's a classic engineering trade-off. On one hand, you have the phase-shifted full bridge, or PSFB. Think of it like a heavyweight boxer. It's incredibly tough, super robust, and can take any sudden punch the system throws at it, like a cooling fan kicking on. On the other hand, you have the LLC resonant converter. This one's more like a world-class marathon runner, insanely efficient, but only when it's cruising at its perfect pace. Now, for a construction truck where conditions are anything but predictable, you're going to bet on the boxer every single time. So how do we move all that power around? Well, that's where these come in, the high-voltage harnesses. You can't miss them. They're always bright orange for safety. And the arteries analogy is perfect. These cables are carrying the lifeblood of the system. But here's the catch. These arteries have to survive in probably one of the most brutal environments you can think of. Constant vibration, chemical splashes, mechanical stress, you name it. And you can't just grab any cable off the shelf. Sizing these is an exact science. I mean, just look at the difference here. The wire feeding the DC-DC converter are relatively small 10 square millimeters. But the main feed coming from the battery pack, which has to handle a massive amount of current, we're talking 70 square millimeters. That's a cable 7 times thicker, and it's absolutely necessary to handle that power safely without overheating. So all of these high-voltage arteries have to connect somewhere, right? They all lead to this central hub, the High-Voltage Junction Box, the HVJB. And if the cables are the arteries, then the HVJB, well, it's kind of like the heart and the central nervous system all rolled into one. It's the traffic cop that safely distributes power and, just as importantly, protects every single high-voltage component with a web of fuses and contactors.
Okay, so designing and building all this amazing hardware is one massive challenge. But getting it legally certified to be sold and used all over the world, that's a whole other level of difficulty. We call it running the gauntlet for a reason. It is an absolute maze of different, sometimes conflicting, global safety standards that every single piece of this system has to pass.
And what makes it so tough is that every major market has its own priorities. You look at Europe with ECR 100, they're laser focused on battery safety and making sure nobody can accidentally touch anything high voltage. Then you go to the US. Their FNVSS 305 standard is all about post-crash safety, making sure the high voltage system instantly shuts down and becomes safe after an accident. And then China's GB/T standards, they add another layer, demanding continuous insulation monitoring and super strict waterproofing. The real trick is you have to engineer a single system that satisfies all of these different rules all at the same time.
So, with all this high voltage, how do you make sure a mechanic can work on the truck safely? Well, that's where this incredibly clever feature comes in, the High Voltage Interlock Loop, or HVIL. It's actually a low voltage circuit, a simple little loop that runs through every single high voltage connector. So, if a technician ever tries to unplug a high voltage cable without following the proper shutdown procedure, the very first thing that disconnects is this little safety loop. The moment that loop breaks, the main vehicle controller instantly kills all high voltage to the system. We're talking milliseconds. It's an absolutely critical, life-saving safety net.
Okay, we've talked a lot about hardware and safety. Now let's get to the brains of the operation, the software and intelligence that makes it all work in harmony. And it truly is like a symphony of power coordination with one conductor leading the whole orchestra, the Vehicle Control Unit, or VCU.
The VCU's very first job, every single time, is to manage a safe power-up. It's not like flicking on a light switch. It follows a very precise, carefully choreographed sequence. First, it does a self-check on that HVIL safety loop we just talked about. If that's good, it uses a smaller relay to pre-charge the system, slowly bringing up the voltage to avoid a huge damaging current spike. Only when everything is stable and ready does it close the main contactors and make this system fully live. It's a four-step dance it does flawlessly every single time. But where the VCU really earns its keep is in power arbitration. It has to act like a triage doctor, constantly making tough calls when battery power is limited. And this chart lays out its logic perfectly. What gets top priority no matter what? The ePTO, the motor spinning the drum. Why? Because if that drum stops turning for too long, the concrete inside will harden, and that can literally destroy a multi-thousand-dollar piece of equipment. So keeping the concrete mixing is priority one. After that comes keeping the essential 24-volt systems alive. Then, maybe, you can use power to move the truck. And what's at the very bottom of the list? The tab and air conditioning. Sorry, driver, but that's the first thing that gets sacrificed. And really, this quote from the core engineering spec just says it all. The quality of the concrete is paramount. Everything we've talked about, all the complex hardware, the clever software, the layers of safety, it is all designed around that one single non-negotiable principle. The engineering has to serve the mission. And in this case, the mission is perfect concrete. So we've designed and built this amazing machine. But the big question is, where does this all go from here? Because you have to understand, this technology isn't the final destination, not at all. It's a hugely important stepping stone in a much bigger revolution that's coming for all heavy machinery. And that next wave of innovation, it's already taking shape. We're moving towards 800-volt architectures, which means faster charging and lighter, thinner cables. We're seeing new materials like silicon carbide and gallium nitride that will make the power electronics smaller and way more efficient. We're even talking about predictive energy management that uses GPS to know exactly how much power it'll need at the job site. But the coolest thing? Bidirectional converters. This means the truck doesn't just consume power, it can actually become a mobile power station for the whole construction site. Just incredible. And that really brings us to a final, pretty powerful question. Think about it. We've just taken one of the noisiest, dirtiest, yet most fundamental vehicles in all of construction, and we've engineered it to be quiet and emission-free on site. So if we can do that, if we can completely reimagine the humble cement mixer, what else in our cities is just waiting for its own electric revolution?